开始，好。
Okay, hello everyone. Welcome to today's nice talk. We know recently self-evolving algorithms have been a very popular algorithm, and researchers try to explore a method to continuously train larger model or AI agent without manual supervision. And today, I'm very pleasure to have Zhenrui here to give his presentation about the paper Dr. Zero, self-evolving search agents without training data. And let me first give a brief introduction to Zhenrui. Zhenrui is a final year PhD candidate at UIUC, and he has broad interest in natural language processing, recommender systems, and information retrieval. His current focus lies in the developing of high-performance, efficient, and robust large language model and vision language model, with an emphasis on domains such as intelligent agents, conversational systems, and recommendation. And I'm today's host. I'm Da Wei, and I'm currently a second-year PhD student at Arizona State University. And my research focuses on large language model and data mining. And yeah, now, Jerry, could you share the screen and start the presentation?
Okay, sure. Can you see my screen and slides? Oh, sorry.
Yes.
Okay, nice. I'm just going to get started. Just a second. Okay. Yeah, my name is Zhenrui. I'm a final year PhD student at UIUC. So I'm happy to be here presenting the paper Dr. Zero Self-Evolving Search Agent without training data. So this is a collaboration between Meta and the UIUC. I will just get started. So before we introduce the contents of Dr. Zero, I will first quickly talk about the evolution of LLM post-training. So nowadays for LLM post-training, so usually if you start from a base model, you will usually have 3 stages, and which is basically supervised fine-tuning, which gives the model initial capabilities on instruction following. And then you have some sort of preference optimization. Either you use DPO or use online RLHF methods. And you would also have an additional stage of RLVR, which is basically improving the model's reasoning capabilities with verifiable rewards. So this will mostly go into domains like math and coding. And this will give you then a post-training framework where the model would perform pretty good on instruction following and along with reasoning intensive tasks like math and coding. So yeah, this is basically the state of LM post-training. And this is also a paper from, by the way, I forgot to introduce. This is the 203 paper, which came out in 24, was from the Allen Institute of AI. And similarly, this is the OMO3, also a fully open sourced model in which they actually release both the training data, training pipeline, and the model weights. So for OMO3, they have done very similar things, but they have shifted focus to from the algorithmic design to more and more to the high quality data. So in this case, you can see that they have started from pre-training, selecting high quality pre-training data from a web, and then they also have high quality long context pre-training data. And following that, they will use some sort of SFT to give you think and instruct models depending on different sorts of tasks and data sets they use to post-train the model. And they also follow DeepSeek R1, where you directly from the base model to train directly train a reinforcement learning model that has relatively strong reasoning capabilities, which they call OMO3 RL0. So you can see the shifting from the algorithmic design to the curation of high quality data, and the role of getting these sorts of high quality supervision is getting basically more and more important as the model capabilities evolve. So this leads us naturally to the question: is it possible to let the model craft its own data and train itself? As the model are having much better capabilities these days, is it possible to find a way that to let the model generate high quality data and let them train themselves, right? So in the old days, you have supervised training, in which you have to have both the prompts and responses to train the model, along with the reasoning trajectories maybe. And nowadays, you can have verifiable rewards, which you only have the prompts and the final answer to basically generate rewards. And is it also possible to let the model to generate the prompts and labels themselves and let it train on its own? So it turns out it is possible. So I will introduce two important pioneers in data-free self-evolution. The first one is Absolute Zero. So Absolute Zero basically uses a single model to act as both the proposer and solver, and it interacts with the coding executor environment, so that the model is trained through the RL to basically generate upon a seed subset of coding questions, and to generate more and more harder questions for the model for the model to solve, right? And the model itself is the proposer and the solver. And so after generating such questions, you will let the model to train on these generated coding questions to see if it can perform well on those. And then you basically form this as a self-evolution feedback, and then let the model to basically involve iteratively as the proposer and the solver. So this paper focuses on the coding questions, which relies on a coding executor environment to craft verifiable rewards and let the model self-evolve. And similarly, there is a second paper which is called R0. So R0 takes a slightly different approach. R0 will generate training data through a challenger role, and then let another solver to actually solve the problem. So in this case, they actually use two different models. The initial model will be trained to maximize the challenger reward, which basically encourages the model to generate more challenging questions, and the solver will try to solve them, right? But this kind of work is also focused on verifiable domain, and then it actually uses majority vote to train the model with reinforcement learning. So with majority vote, then the model is basically you're basically assuming that the model would do right when the majority answers are aligned. So this is the second paper. But what about knowledge tasks? For knowledge task, we know is for LLMs, we know it's easy to generate simple questions, but very hard to generate hard questions. So that is, if you ask the LLM to generate questions, it will usually have very simple one-hop fact-seeking questions, like let's say who is the president of the United States? These sort of questions, which is basically very simple for LLMs, especially search agent, to solve these days. And even with when augmented with search engine, we see that the current data-free methods, they do not perform so well on knowledge-intensive tasks. And that is particularly the case for multi-hop benchmarks like music or Bambugo. So these two are the baseline methods that we started from, and then we augmented this method with a search engine to let them basically train as a search agent rather than the pure model itself. And we still see that when you let the model to generate questions and train themselves, the generated questions are usually very narrow regarding the domain and the style of the questions, so that the model can learn something, but it doesn't really learn that much. And the majority of these gains are actually on the single hop questions, like you can see natural questions, trivial QA, or pop QA, where the models have more improvements, but on multi-hop benchmarks like music, 2Wiki, MQA, then the gains are relatively marginal. So that leads us to the next question. So how can we generate diverse and challenging questions and along with verifiable answers? So this is basically the most important part of self-evolving, especially data-free self-evolving agents, because without reliable and diverse and high quality data, you're going to basically have trash in, trash out, and the model is probably not going to learn that much. So, based on our experiments and experience, we have basically two things we think is particularly important for crafting diverse and challenging questions. The first is the seed. If you give the model a fixed prompt and let it generate questions, you will almost certainly have one-hop questions if you don't have any well-formatted instructions and a seed corpus. So this is why we directly sample a search snippet from the search engine, and then we use it actually as a seed document to basically improve the coverage across the topics and domains. So this case, the model will actually be able to generate more diverse and more high quality data that covers multiple domains rather than just simple fact-seeking questions. And then the second thing is to make questions more challenging. It's actually very, very important to incorporate the search engine or the search function for the model to bridge to the next entity. For example, if you want to craft a challenging questions, the usual case is to craft a 2-hop or 3-hop questions. I can give an example for who is the president of the let's say biggest country in South Asia, right? So this is a typical 2-hop question where you have to first identify the country and then search for the present name of that specific country, right? So if you don't have a search engine and let the model to self-generate multi-hop questions, many of the cases are unreliable or even hallucinated. So this will give you very low quality data, and then train on these multi-hop data will usually give you very bad performance on actual benchmarks. So therefore, the solution is pretty simple. You would need a search agent as the proposer. So the search agent can start from a randomly scraped seed document, and then from that document, the model can start from some entity and then use some associated properties to connect to the next entity, or do some external search to make a parallel multi-hop reasoning, and then craft a question based on these basically the cross-hop relations between these different search results and the initial seed document. So we use the search agent as the proposer, and we begin with the selected entity from the seed document, and then we slowly and gradually expand the reasoning chain to actually craft a hard, challenging question. And the second thing is verifiability. So unlike math, we do require some processing for open domain question answering. So an example is probably who is the president of United States, right? You can answer this with Trump, you can answer this with Donald Trump or Donald J. Trump or DJT, and all of these are actually correct. And so it's not like math where you have basically a LaTeX formulation, and that's basically the only solution. So we start to derive the question from the answer. Therefore, we basically force the model to say you have to select the entity from the original search text as that entity as the answer, and the resulting output will form a complete XY pair by design, where X is the question and Y is the answer. And in addition, we also require at least one solver predictions to be exactly the same. So we use exact match here to be correct, so that we doubly ensure the verifiability of the generic questions. And that naturally leads us to the reward design of the proposer. So we want the model to basically generate harder questions so that the model can learn more, right? You know, for simple questions, most LLMs can already do well. So we propose this very simple rewards, which has a 0 variance filter. So that is where when the solver when none of the solver get this question correctly answered, then the reward is 0 because it's too hard. That's not manageable by the solver. And at exactly one correct prediction by the solver, and then you will actually have the highest, you will have the peak reward of 1. And then we let it to linearly decay up until the n, which is the group number of the solver. That is saying the more you predict it correctly, the less reward you will get. So that what we hope the solver to learn is that the model should generate more difficult questions, but to the extent that the solver can still answer it, right? So this is how we basically generate verifiable but still challenging questions. And for the solver to learn, this is relatively easy. We use the data provided by the proposer and then just do standard GRPO training on the solver to enhance its question answering capabilities. So that's the proposer and solver reward. And then we want to talk about the nested sampling, and which is the cost of rollouts. So you see, for this sort of nested sampling parts, when basically you have a question proposer. The proposer will generate m rollouts, and then you also have the solver. The solver will have to answer n times for each of the questions, right? So this is a sort of a nested sampling process. So the total rollouts would basically be m multiplied by n plus 1. So this, even if you have very low m and n, like 4 and 5, this could easily be over 20 or even 30 or even 60. And this will actually gives you very high computation for the entire rollout to finish. So each training step can take something like hours. So that's what we have. So that was what we started initially from, and then we find that this is computationally infeasible. So is it possible to reduce the number of either m or n and still getting reliable rewards? So we basically come up to the solution of hop group relative policy optimization. So before trying the HRPO approach, we actually also tried Reinforce++. So Reinforce++ has a global baseline, right? You can see that one of the versions of Reinforce++. But if you use the global baseline, you can see this is very unfair for simple questions, because the reward design for our method is basically encouraging hard questions. And then basically all the simple questions are filtered out if you use some sort of global design. And most of the questions then you end up with is very difficult questions that are very hard to verify, and the solver model often gets it wrong. And so the learning signals actually get reduced. That's not what you want. So instead of doing a global baseline, what we do instead is that we cluster the problems by their structural complexity. So basically how many hops you will need to search before you can get to the final answer. So this is basically one hop question. You need to at least search once to get the facts that you need to answer the questions, right? So we cluster all of the questions in the batch with this sort of a structural information, which is n hop questions, right? And we then compute the advantages within these clusters to establish a calibrated baseline. So for simple questions like one hop questions, you have a baseline, and then for two hop questions, you have a baseline, and etc. And so on and so forth. So that this creates a relatively balanced baseline for each sort of questions, so the model can learn from simple questions as well as hard questions, so that you end up with a model that can answer both simple and hard questions, and then the rewards are also provides the best learning signals for reinforcement learning, unlike a global baseline that you will have like Reinforce++, right? So this is then HRPO, how we propose to train the proposer. And luckily, we also have the question hops information, because you see, we build the proposer ourselves, right? We have the entire thing and how many searches it actually performs to reach to the final question, so that we also have that information, which normally in training data you don't have these sorts of metadata to perform it. But because we are a self-training feedback loop, we can have all sorts of information from both the solver and the proposer, so that we were able to do it with HRPO. And finally, this is basically what HRPO look like. So the proposer is the hop group relative policy optimization. You can see we use theta to basically denote the parameters. And then for each batch, we will sample from pi theta, which is the proposer model. This x, y are the proposed questions. And then we only sample one question per prompt, right? So this is because of the hop group thing. You don't need to sample multiple questions per prompt. And then for the answer, we still follow the GRPO. So here we sample n predictions from the solver. The solver is denoted with the phi. So phi is then another separate solver search agent, and then the R basically denotes the search engine. And then we sample one question per prompt from the proposer, and n predicted answers for each of the questions from per prompt, right? So that would actually gives you a n+1 complexity rather than the originally squared complexity for the rollouts, which is much cheaper. And for training, we use a on policy setting, so that you see we don't have any clipping here. So this is just the log probabilities of the model, and then we also apply the KL divergence to ensure the model trained stably. And more importantly, the advantage is basically computed with the reward, but minus the expected reward of that specific group. So you see the IH here. H basically is the hop number that of that specific cluster, and and then we compute the advantages for each of the clusters, and then those advantages are then used to update the model parameters depending on if these are positive or negative advantages. And yeah, that's pretty much about HRPO. And you can see here we generate one question per prompt, and then multiple predictions from the solver. Yeah, and for the solver model, we use standard GRPO, which basically is the same. We sample one question and answer from the proposer model, and then we also sample n from the model. And then when you update the model, we will actually do some clipping like the standard GRPO would do. And finally, with the KL divergence as the penalty term, prevent the model from collapsing. So this is basically what Dr. Zero looks like. You see, we have a proposer. The proposer is the model itself, right? We equip it with the search tool, so it becomes a search agent. And we'll let it reason and search multiple steps. So this is multi-step rollouts until it generates QA pairs. And of course, these QA pairs are basically one question per answer. And these are denoted with a question and answers. And for the solver, we will also let it to perform reason and search. And for each of the question, it will generate multiple predictions. And some of these predictions are wrong, some of these predictions are correct, right? And we use that to compute the difficult reward. The difficult reward picks at one, exactly one correct solver predictions. So that difficult reward is going to use to update the proposer model. And because we have sampled this multiple rollouts and the answers, we can use these as the outcome rewards, and then use the outcome rewards to update the solver model with GRPO. So this basically forms the self-evolution feedback loop. Okay, then that's pretty much everything about Dr. Zero. I will go ahead and introduce the experiment settings. So for the corpus, the search engine, we use the same as search R1. We use the English wiki dump. We use the E5 base, and we retrieve 3 document snippets per tool call. And for training data, there's none. For the we use the proposer generated data to train the solver. For evaluation, we use a mixture of one-hop and multi-hop questions, and the metric is exact match. So this is the main benchmark results. We can see that the first part of the table is then 3B, and the second part of the table is the 7B. We're comparing to both few shot baselines and the SFT and supervised baselines. So there is no data-free method, which means that this is not a fair comparison here. So you can see that the first few prompting our COT search R1, these are the few shot prompting methods, and then the rest of the baselines are supervised which are trained on a mixture of NQ and hotspot QA. So we can see compared to the supervised baselines, Dr. Zero actually performs quite well, especially on one-hop questions. It outperforms all of the baselines for the 3B models. And for some of the, for multi-hop baselines, it basically can perform similarly or even outperforms these for many of the benchmarks. If you can look at the 2-week MQA for the 7B model, this is because 7B model have better capabilities at generating harder questions. This is also what we observed. So we have consistent observations for 3B and 7B models where both models can self-generate data and train on those data and perform similarly or comparatively to supervised agents. So this basically validates the idea that self-evolved LLMs can perform pretty well even without any supervision. Any supervision means both the prompts and the labels, so non-data. And this is the training dynamics of the Dr. Zero. So because all of the prompts, questions, and the rollouts are sampled from the model, so we actually found that the model actually trains very, very fast. So the most substantial gains are already from the first iteration, as you can see here. We start from the solver and the proposer. We start from the proposer training and then followed by the solver training, right? You can see that for each of the iteration, for all of the 3 iterations, the most substantial gains are already realized during the first iteration. So the second iteration gives you a little bit more gains, and for the third as well. But for the 7B model, we actually found that 2 iterations already use the best overall performance. So that's saying that about 100 steps of training will already give you a very good performance. So this is then the further results of different iterations. So you can see for the 3B model, training in 3 iterations actually give you more performance gains, but for the 7B models, 100 steps of training is already giving you the optimal performance, and which is comparably matches supervised search agents in this specific case. And we also compare to the data-free baselines, which is what we showed in the beginning of the slides. So we see that Dr. Zero can consistently outperform the baseline methods, and the baseline methods are also augmented with search to ensure the fairness. And but we can do it with significantly reduced compute, right? Remember, we train a model with HRPO, so that you, for each of the rollouts, you're basically rolling out one more compared to supervised training alone, right? And for R0, you actually have to do the nested sampling where you have generate M examples and then and predictions per those generated questions. So that was very expensive, and the gains are also more substantial on multi-hop benchmarks. Like I mentioned previously, the self-generated questions are often not diverse enough, but with the help of search agents and HRPO, we can actually generate much more diverse data and much more challenging data with multi-hop constructions. And the gains are especially significant in larger benchmarks like 2-wiki, multi-hop QA, and think documents. And we conclude that these gains are mostly from good instruction, where we basically tell the model how to generate multi-hop questions, how they should perform search, and then how the final question answer pairs should look like. The C document, which also significantly help with the diversity of the generated questions, and finally the difficulty and format reward. Those are also key factors for improving the performance of the self-evolving search agents. So yeah, that's we can consistently outperform baseline methods. And we also actually check the ratio of synthetic questions, right? Because we can manually control the, control the proposer, we let the proposer to generate different ratios of questions. So here we use 1 hop, 2 hop, 3 hop, 4 hop as the ratio, right? So 1 to 1 to 1 to 1 is basically 25% 1 hop, 25% 2 hop, 25% 3 hop, and 25% 4 hop. And then for the last ratio, 4 to 3 to 2 to 1, then that's actually generating more 1 hop data, and then a little bit less 2 hop data, and more and even less 3 hop and 4 hop questions. So interestingly, we see that for the 3B variant, increasing the 1 hop questions actually improve the overall performance. You can see the ratio 4 to 3 to 1 to 2 to 1 gives you the best overall performance compared to 1 to 1 to 1 to 1. So this actually tells you that weaker models, they actually learn better from more simple questions, right? Because their intrinsic capabilities might not be strong enough to directly handle very hard questions. So you do want a lot of simple 1 hop questions so that the model can learn from these learning signals and improve its search capabilities. But for the 7B model, the case is slightly different. For the 7B model, if you look at the multi-hop benchmark like HopHop, QA, 2Wiki, 2Wiki, multi-hop, QA, and Music. So all of these multi-hop benchmarks, they actually improve with more proportion of higher hop questions, more challenging questions. So this suggests that the 7B performance would actually benefit from additional multi-hop synthetic data if you want the model to focus only on challenging multi-hop complex queries. So that's the ratio of synthetic questions. And we also did some ablation. I think this is, I'm sorry, this is probably the wrong slide here. So we did some ablation, which is basically indicating that our previous conclusion of the gains, the majority of which come from the good instructions, the C document, the difficult, and format reward. So we will have more of the ablation results in the paper. And finally, we have some qualitative examples. So this is the reasoning patterns of the proposer. So we start from a specific entity with the C document, and sequentially we'll build a factual chain and then use formative reasoning and the external search to basically construct a reasoning chain, and finally yield a verifiable, concise answer. So the following is one of the example here. We'll also use the question/question, answer/answer format here, and we omit the previous steps. But actually, there were 2 or 3 steps in this particular case, which basically follows the react, reason, then act format of a search agent, and before it used the final question-answer pair. So that's the quality example. So finally, the conclusion takeaway. So we see that Dr. Zero achieved robust gains on knowledge tasks by scaling compute rather than the data, right? So if you scale the model capabilities, you usually would either increase the data quantity or the compute. And we actually show that by scaling the compute alone rather than the data, you can also improve the model performance to a level that is comparable to supervised agents. And the Dr. Zero relies on 2 search agents, which is the proposer and the solver. 1 generates questions, 1 answers them. And this continuous interactions basically forms a self-evolving curriculum. And by proposing the additional HRPO training algorithm, we cluster the questions by difficulty, and therefore significantly improves the sampling overhead that you would usually see for nested sampling, so that you will get the actual difficulty rewards from the solver model. So that was significantly less compute than standard rollout methods like GRPO. And finally, we see that Dr. Zero can match or even surpass fully supervised search agents on complex open domain knowledge benchmarks. So this also showing that high-level reasoning can emerge purely through self-evolution. So yeah, I think that's all the slides I have. So yeah, thank you very much.
Yeah, thanks, Zhenrui, for this very impressive presentation. And for the audience, if you have any question regarding, let's say, self-evolving search agent or anything about this paper, just feel free to share it in the platform. And I think we have plenty of time to do the Q&A session with Zhenrui together later. And I think we already collect some questions from our audience, but before that, maybe a very general question regarding self-evolving algorithm. The question came from Twitter. It claims that maybe in the year of 2026, we're able to achieve so-called self-evolving agent. And I think there are several types of self-evolving agent, but this type of self-play algorithm during training, I think is definitely one of the most important ones. So what's your opinion about this kind of self-play with a proposer or solver, this type of paradigm? What's the limitation and maybe how can we advance this type of paradigm?
Yeah, I think that's a very good question. That's also a very fundamental question. So I think self-play is generally pretty useful if you want to improve a LM or improve agent's performance, and especially if you already have a good prompts, right? So and then you could do self-play on those prompts. So that was already proved to be effective. I think back in 24 there were the self-play papers there, and then here what we are actually trying to show is that the self-play or the self-evolution, self-improvement sort of algorithm can also work even without the prompts, right? So we're trying to let the model to see if they can craft diverse and high quality data that can use them to train themselves, right? So then you see there is a closed curriculum where you don't actually need any sort of external feedback except for the tool, right? And then the model would basically act as a data flying wheel, and then it would just basically grows better and better and better. And of course, this is a very initial and very early efforts to explore data-free self-evolution. But I think if you have both good prompts and then you also let the model to generate a lot of synthetic data, so I'm pretty sure a lot of companies on training LLMs already use a lot of synthetic data. But if you let the model to generate the synthetic data themselves to train themselves, this is also doable for a lot of tasks. And if you're also able to collect more high quality human data, I think the gains will be even more significant than the data-free methods themselves. Yeah, does that answer your questions?
Yeah. Thanks for the answer. Yeah. I think it's a very interesting perspective to try to compare, for example, nowadays proposer solver paradigm with self-instruct. Because I think self-instruct is something published 2 or even 3 years ago, right? And then after we have RLVR, right? There are suddenly a lot of paper about how to improve large model capability to generate question or task. So I think from my perspective, it's like, okay, for example, previously when we use SFT, maybe we need both question and response. So we do something about how to synthesize high quality response. And later when we have RL, people find, okay, we don't need the response, right? We only need the answer that could be verified. And we just need the question. So people start to explore, okay, if we can just let larger model to synthesize question itself. But I think it's very impressive to me. I think it's like, how can we use larger model to automate the training process, maybe with less and less human effort?
Yes, exactly. I think that's a good point. So I think maybe for very hard questions like the ADOS problems, so these sort of prompts or this sort of initial data is still very important for frontier labs and how they do self-improving language models. But I think with the evolving of language model capabilities, I think the models will be able to generate themselves more and more high quality data, and eventually maybe all of the LM will probably train on synthetic data one day.
Yeah, I totally agree. Yeah, at least a lot of them are used to train nowadays larger model, and more of them will be used to train future larger model.
Yeah, exactly.
Yeah. So yeah, let's go back to some audience questions. So I think the first question is a very specific one, and the question is, can this work be applied to maybe financial and trading domain, and any suggestion on how to apply it? And I think maybe the question could also be, for example, how to apply or what type of domain, what type of characteristics in that domain maybe is appropriate to apply this work into. Yeah.
Okay, yeah, I think that's definitely possible, right? I do know there are a few data sets like FinQA, which is a finance QA data set, I'm not sure if the purpose of this agent is to do more trading or do more sorts of finance question answering. So, but for these both of questions, if you're talking about FinQA, so there is actually a lot of the things that you can directly use from Dr. Zero, and then you can directly apply that to the specific domain or construct your own search engine or your own embedding model, and then to let that train your finance agent. So I'm pretty sure that will work. And for trading, I'm not exactly sure. So I've already seen by now there are a few benchmarks or competition for different LLMs, and let them trade either stocks or cryptocurrencies. And a lot of models are actually already doing pretty well for those closed source frontier LLMs. So yeah, I'm not really sure if they could learn much from the financial market, and especially if you already have the financial market, the prices, the stock prices every day, those can be used as data. So I would say that would definitely work. But financial market is mysterious and no one really understands how those work. So
Yeah, that's
yeah,
true.
but
Yeah.
I think that this is definitely a good direction. So maybe we can at some point we can make money just with finance agent someday. Yeah, I'll be glad to hear that.
Yeah, I think it's very doable because if we think about the paradigm, the proposal solver paradigm, actually we don't need any existing data, right? We can let large model to produce a question to improve the both question generation capability and the solving capability, right? So I think there should be very little limitation in applying it to some other domain specific area. Yeah. And
Yes, exactly.
yeah, let's go to the next question. So here's the question is about like how much computing resource is required for self-evolving research, and also do you suggest, for example, master or PhD student who don't have a lot, don't have the access to a lot of computing resource to conduct this self-evolving research?
Yeah, so for my case, this was done in collaboration with Meta. So I was sort of like a research intern at the Meta. Even at MSL, we have relatively limited computing resources back then. So we for the experiments, we were mostly training on one node, and each node comes with eight A100 or eight H100s, right? So each of the nodes came with 8 cards. So that's pretty much the resource we got. So we were only able to train a 7B model, and you also have to consider that we actually use a more efficient method, which is HRPO compared to the GRPO to make this to make all of the experiments. So the final experiments will probably take 2 to 3 days or 4 days to finish. So I would say if you still want to train the model to make them self-evolve, this is going to be rather resource intensive. So I suggest you seek some sort of outside resources like with companies like Meta and Amazon, and to get computational resources if you want to do this sort of RL agent training. Because we all know that RL training, the rollouts can be extremely long, can be extremely time requiring, and not to mention the model sizes, right? So yes, unfortunately, that's still going to require some GPUs to make it work. But at the same time, I also think there are purely test time scaling methods for self-improvement. So if you look at recent improvements like the recursive language model or other sort of test time scaling methods, we should basically exploit what LMs can do and then split those into simpler recursive manner to make LLMs to solve them. So I think this is also a possible way to let the model self-evolve at test time, right? So you let the model with some sort of algorithm or a recursive method, split the task into subtasks and use sub-agents and coding environment, etc., to basically let them find better ways to solve questions at test time. I think that's also one possible directions to perform self-evolution, and that's test time only, and it's going to be much more simpler than training a lot of if in the case that you don't have particular or enormous GPUs. So I think that's also one potential direction that's worth pursuing. So yeah, I hope that's helpful.
Yeah, it's really a good point because I think test time evolving is also a very important part. And if you compare it with this self-play or training time self-evolution, I think it's all about how to leverage larger models' previous experience, right, to improve larger model, no matter it's during test time or training time. So yeah, I agree. If you don't have enough resource, maybe you can try to do something during the test time rather than training time.
Yeah, exactly. I think test time scaling is still a lot of things we can do, especially after the recursive language model came out. I think that was a pretty novel idea. Yeah.
I agree. Yeah. And let me see if we have any other questions. Okay, maybe I can ask another question more specifically for this self-synthetic question. So basically, I think nowadays we have more and more paper about self-generated question, no matter it's like paper like absolute zero or paper like R0 or self-question LM. But my question is, if we really think about it, so the question generated by larger model, actually, if we think this problem from a data distribution perspective, the question generated by larger model should be something it's familiar with, right? Maybe something larger model have seen during the training time, right? So if we continuously or iteratively use this kind of self-generated question to train the larger model, no matter we use RL or SFT, is it possible that larger model may be stronger and stronger in the area it's familiar with? And it also lets larger model to be weaker and weaker in the area it do not have a lot of experience during the, for example, pre-training time. Is it possible? And so how can we maybe mitigate this kind of limitation?
Yeah, I think that's definitely a valid concern. So if you let the model to generate things, then because we're sampling based on probabilities, right? So inevitably the model will generate the stuff that is generally more familiar with, and less with the ones that is less seen during pre-training or mid training, right? So yes, that is a valid concern. So how? In our specific case, we sort of solve it by the seed document, right? So we also observe that this is a very important case. If you do not have any sort of seed document that you randomly sample from a search engine or from your corpus, then the generated questions will be very similar. All of those will be fact-seeking questions grounded in a very relatively narrow domain, and the question will perform really good on those simple questions, and then the model will eventually fail on other sorts of questions and open-end generations. So we try to mitigate that questions by, for example, introducing the search agent. Search agent is basically incorporating the external information at the rollout, and then try to to let the model to ask the questions that it to let the model construct reasoning chains to entities or to events that it's not particularly familiar with. So that's what we are trying to do here, and we believe the search agent and the initial seed document have actually significantly helped with the diversity of the generated questions. So yes, and for other sort of domains like math and coding, because they already focus on relatively narrow use cases, and so I think that's not really a big concern for the R0 paper, right? So for example, those papers, you can see they focus on very specific math problems like AIME or math. So the model would also be able to self-evolve really quick on benchmarks. But unfortunately, I'm not really sure if those trained models would perform much worse on other domains. If that was the case, I'm not really sure. But I think this is a valid concern that if you let the model to sort of train on its own generated data, and then the entropy will go lower and lower and lower, the model will become more and more confidence in that specific domain, and this would inevitably lead to model performance drops on other domains. So if you want to post-train a model with some sort of self-improvement, I think how you select and filter the data will be eventually very, very important to control the overall performance on different downstream tasks. I think that's also what Frontier Labs are working with, how you basically distribute and how you arrange the different domains of post-training data so that you get the overall well-performing LLM. So this is also a very hard question, and how you attribute those gains to different data. This is a very important questions that still remains to be answered.
Yeah, exactly. Yeah, and I think it's a very interesting perspective to let's say, solving this problem from the seed data perspective. Because seed data is like manual annotation or manual supervision, right? So maybe we need at least some of them to avoid larger models bias to be accumulated, right? So I think, I remember there's another paper also from Meta. Its name is not self-evolving or self-play. It's about how can we leverage minimal human effort to let larger model to continuously evolving. Yeah, I think it's a very good perspective. And I think a very natural follow-up question would be, let's say, for the seed data, you use it in the very beginning, right? So is it possible we continuously, like, say, inject some human supervision signal? For example, we augment the seed data, or we add some human intervention in the self-play or self-evolving algorithm.
I think that's a good point. I want to clarify that the seed data I talk about is actually a random text snippet from the search engine. So that's not really human supervision, but yeah, it's still that's still data. So that's why we in the title we said without training data rather than without data. Yeah, rather than entirely saying we train without data, because we have a search engine, right? So the seed document is basically a seed snippet is basically a short snippet that you can get from Google search or from the search engine. You have some paragraph, right? So we in the initial prompt, so that the model can generate different questions, right? So if you for each of the prompts, it actually starts from different prompts. We have some instructions and then followed by this seed snippet. So and then the model will generate starting from an entity from that seed document. And so this is not human supervision. But to answer your questions, I do think incorporating human supervision can further help the model to grow in capabilities. So imagine if you're doing some sort of coding agent. So everybody uses cursor or anti-gravity these days, right? So without the human feedback on those trajectories, right? You have a session, and then you will let the model to at least know if it does what you want, and if it does not what you want. If it does not did what you want, you will usually ask the model to do something again, right? And you basically are mixing these human instructions and feedback into this very valuable and usable trajectories, and then I'm pretty sure that they're going to more or less use these to train the next Claude model, and then to let them actually improve on performance, right? But initially, if you back into Claude 3.7 and even earlier versions, they are significantly worse than what it is capable of doing now. So I don't know how they train Claude, but my guess is that they extensively use this sort of human input, and which also acts as some sort of human feedback on these trajectories. They select the valuable ones, the long ones, and the hard challenging ones. Then they train the model, and then let the model to become more and more capable. And then as the model become more and more capable, we are also using it for more and more demanding questions, more and more demanding tasks. Let the model to generate something given like a VS Code, right? And these and then the model does well on eventually this is also some sort of self-improvement, right? But with human feedback on that specific loop, and then the model would eventually get better and better at some sort of tasks. So does that answer your question?
Yeah, it's very insightful, I will say. Yeah, I think it's very important to think about what type of feedback from human is actually needed, right? Maybe previously
Yes.
we just need some binary preference label, and now maybe when larger model becomes stronger and stronger, maybe we need to think about how can we, for example, propose more challenging question to them, or give more feedback and combine this feedback with environment feedback, right, to update the larger model. Yeah, I think it's very insightful to think from this perspective.
Yes, and human feedback is mostly implicit these days, right? So you must infer to basically see if the user is very happy with the trajectory outcome, and then sometimes you probably have to still have to do some filtering, and then some other sorts of processing before you can really use those trajectories to train the next model. And I think, but that's basically the path of how coding agents evolve to today, to Opus 4.6, and how they eventually get this good at coding.
Yeah. I agree. Yeah. Okay, let me see. All right, I think that's all the questions from our audience and myself. Yeah, and thanks again to Zhenrui for this very impressive talk. And I think that's it for today's presentation. Thanks for watching.
Nice. Thank you for having me. Thank you.